Okay, hello everyone. Welcome back to Deep Learning Systems Action Implementation. So this is lecture 8. In today's lecture, we're going to walk you through on some of the detailed implementations of neural networks through our IPython notebook. And it's going to cover a lot of the contents of specific implementations of what we discussed in the last lecture. Again, this is going to be an implementation section, so I'm going to use IPython notebook instead of slide to walk you through some of the specific content here. As a first step, you will need to run this code block. In here, so if you run it for the first time, you want to uncomment this particular code block that clones up this lecture 8 repo onto your local. And then after that, you will be able to do some of the local modifications to continue run it. And in the next time, you can just comment this so that you will get kind of a persistent drive of needle repo in here. And we can take a look on the right-hand side. There's already needle being cloned in here. And this is going to be the code that we're going to use for today's lecture. So if you have, in the future, we're going to release homework 2, and the same repo can be used. You can also use this homework 2 repo for completing this piece of code. Another thing that I want to mention today is that for today's lecture, I do have a readily implemented automatic differentiation of needle. So if you want to, but the lecture 8 repo do not contain implementation. So you will need to copy and paste your own implementation of automatic differentiation onto the corresponding file in order to run some of this demonstration here. Okay. So before we get started, let's first do a bit of refresh of needle since lecture 4 and homework 1. So we know that in a lot of cases, we will be able to define a needle tensor in here, and here W is a needle tensor. And one of the things we want to quickly go over is how can we go and update weight in neural network training? And in a lot of cases, we talk about how can we do forward neural network computations, as well as taking gradient with respect to certain parameters. But once we have those gradients, there's always a question of how can we go ahead and update the weight values according to the gradient or according to some stochastic gradient update rules. So let's try to do that. Assume that we have a weight vector here as W and gradient vector here as G. And one thing we can do is we can go ahead and first of all check the weight vector in here. We can find that by default when we create a needle tensor in here, the required gradient field of this needle tensor equals true. Right? That means that we are actually tracking the computational graph and gradient in order to compute a gradient as we start to run some of the computations. So let's assume that we're going to run a stochastic gradient step for several steps. So one thing we can do is we will be able to say take a gradient vector. We can take a learning rate and run this for loop in here. What this for loop does is effectively we're running stochastic gradient descent operations. And one of the things that I want to note in here is that I'm doing like a negative learning rate. So this is because the lecture 8 repo itself does not contain the subtraction operator. But if you have already implemented as part of your needle repo, you will be able to actually go ahead and directly write W equals W subtracting learning rate times gradient. So as a stochastic gradient W. As we talked about in the last lecture, there's one problem with this particular implementation. So what is the problem? The problem is that every W itself actually contains a computational graph because W have this required gradient field being written here, right? So we can look at W the operator. In this case, W dot operator corresponds to element-wise add. And we can also go ahead and look at W dot input, which is another needle value, and you can find that also correspond to element-wise add. You can even go ahead and trace W dot input dot input dot op. So what's happening? So what's happening is that in every iterations, right, we are creating, so whenever we are doing these operations, we're creating a computational graph node that whose operation is element-wise at, right? And then we are saying that, you know, we need to do W plus, and this is learning rate times negative learning rate times gradient in here. And we do another W plus operation here, another thing here. So effectively, we are creating this chain of computational graphs as we start to go ahead and write this weight update rules. And then, you know, in the end, the W we kind of hold at the end of the computational graph. Right? So, of course, in this case, we do get the latest value of W. But what is the problem of this approach? The problem is that, you know, this particular W also takes the computational graph trace of all those previous computations, right? So this is kind of like a common bug that sometimes, you know, people will encounter when you write programs in PyTorch. Imagine that you're doing iterations over several, you know, you are doing things accumulating your loss across several iterations. Then this kind of computation traces kind of accumulates. As a result, the memories of those previous gradient, as a result, you know, usually those gradient also contains like an input computational graph to compute those gradient. Right? As a result, all those input computational graphs get retained through this reference of W, and they cannot get released. So each iteration, the memory cost of the entire process kind of grows linearly as the number of iteration grows. As a result, you will get an auto memory error if you write code in this way. And this is kind of like one of a common bug that you can encounter while writing programs in like an imperative automatic differentiation framework. Okay, so how can we avoid this? So instead, what we really want is, you know, we don't really want to do these updates while keeping track of computational graph. Remember that why do we need computational graph being tracked? The reason is that we need computational graph to be able to help us to perform the reverse mode automatic differentiation, right? So because we know that we might want to compute a gradient with respect to some of the inputs. So we want to be able to, you know, build up computational graphs to help us to track the reverse mode automatic differentiation. However, for the weight updates, we know that most of the cases we don't care about differentiating with respect to the weight update rules. So as a result, we don't need to track the computational graphs in that sense. So instead, we can try to create what we call detached tensor. In this case, you know, w.data is also a shortcut for w.detach, which create a detached tensor that corresponds to the same content, but do not contain the corresponding computational graph attached to them. So if you look at, you know, w.data.require gradient, it becomes false, right? And this, so what's behind the scene is data. We can go ahead and open up the code of Needle and take a look at what's happening here. So if you look at this file, and we scroll down to the w.data, you can find that the data function I simply calls self.detach, where the detach function calls tensor.makeConst self.realize cache data. Okay, so what's happening is actually it's creating a new tensor that shares underlying cache data. So it's not, we're not copying a new tensor, we're creating a new tensor that shares the same underlying memory with respect to the original W, except that we are removing all the additional fields such as inputs and opt field from that particular data that help us to be able to, you know, effectively cut down the computational graphs. So we can also go ahead and take a look in here, right? So if you look at, say, So if you look at here, and I can try to say z equals w.data. And let's check, z.op. You'll find that in this case, z.op actually is none. So you can verify that it's true. Z.op is none. So it does not contain op. It does not contain inputs. This input is empty, right? So, and if you look at, well, it does contain a cache data field. And you'll find that actually this cache data field actually is w.cache data as well. So they do share the underlying data representations. As a result, we're not doing like a deep copy of memory. Okay. So in order to perform updates, what we can say is we can say instead, now new w equals w.data negative learning rate times gradient.data. So if we run this, we can find that we're going to get a new w value in here. In this case, because both w.data and gradient.data are detached, no longer attach a computation graph to them. So if you look at required gradient field of this new w, you can find that it corresponds to false as opposed to true. So the rule that we're having here is actually if we are in eager mode and we're doing arithmetic computations, if all the inputs do not require gradient, then by default we will not construct attached tensor that contains a computation graph, so automatically create a detached tensor. As a result, we can find new w.inputs also equals empty, right? So we can also go ahead and check the code that leads to this piece of logic. If you look at here, we can find that, let me see if it's tensor.make. Okay, this is value, and there is also a tensor.make from op, right? So in here, if it's not in lazy mode, and if in the end, if tensor does not require gradient, usually if tensor does not require gradient, when we initialize it, we'll check if all the inputs require gradient. If any of them require gradient, then this tensor will require gradient. If it does not require gradient, what we can do is we can simply create a detached version of the tensor that effectively runs the computations and ignore the previous attached computation graph. So why does detached tensor is more preferred in this case? The reason is that, in a lot of cases, if you attach the computational graph along with your computations, you hold references to those previous computational graph node or those value node. As a result, these value nodes wouldn't get released until, all the previous reference to that value get released, right? So in this case, we could end up having a long chain of references where a lot of memories that could have been released didn't get released beforehand. So as a result, when you are trying to build some computations, always ask yourself whether or not you can try to not recording computational graphs. In PyTorch, there's also a context of stop gradient or no gradient that serves the similar purposes in here. Okay. So besides creating a new W, it's actually helpful to directly try to update W's content in place way. This is because in a lot of cases, the W is being already referenced, as we will see in the later part. They are being referenced as part of the parameter fields. So it's helpful to directly go ahead and update their values as opposed to create a new variable that then get updated onto the corresponding content. So in order to do that, we can do w.data equal. So effectively, you can try to have a setter that sets onto w.data. And in this case, simply copies the corresponding data content onto the new w in here. And if you look at w again, you'll find that in this case, the w actually indeed corresponds to the new updated weights, right here. So this is the way that we normally use to write our weight update rules. Okay. So now we have talked about the a refreshment of Nino and how we can go ahead and use this in-place mutation. Right? We can try to be able to take a detached tensor, perform operation on them, which again creates a detached tensor, and in placely mutate some of the weight variables in here. As a next step, let's start to take a look at another thing that's going to be helpful in your in building your homework too, and building some modules. They have to do with the numerical stability. So in a lot of cases, and you might have noticed already, like if you look at in here, you can find that after several steps of update, we are getting these values like 0.3999992, right? While effectively every time all we are doing is we are trying to subtracting 0.1 in here. So effectively, it should have been 0.4. If I'm in this case, it should have been 0.4 as opposed to 0.99992. So why does that happen? This is because we are not, when we're storing the data on memory, right? We're storing them through a format called floating point number. And in this case, the floating point number have limited precisions, right? So usually a floating point number contains two parts. There's what we call mantissa part and times 2 to the power of exponential part. So effectively, if you have a floating point number, you will have there's sign bits in here, and you have your mantissa exponent in here. Because you have limited number of bits, right, to represent the sign, the mantissa value and the exponential value. As a result, you cannot expect to express every real number in a precise fashion. That's why when we're doing arithmetic operations, in a lot of cases, you kind of get this arithmetic numerical error when running computation. So imagine that we want to perform softmax, which is commonly used operations in deep learning, right? We are also going to use that in some of our homeworks. Sometimes it might involve a small variant like log softmax as opposed to softmax. So in order to compute this, of course, one of the easiest ways we can go ahead and say, hey, I'm going to directly compute this, right? So the softmax being written as formulas, we are going to take exponential. I'm going to normalize by the sum of all the values in here. So the easiest way we can do is we can naively follow the formula to compute the softmax. For example, if I'm going to import numpy in here, and imagine that I'm going to have input array, it really depends on what the value of input array is. For example, if the input array is like 0.001, I'm going to do the softmax naive here. In this case, you can find that effectively the code first like exponential, right? And it normalizes to z divided by the sum of all the values. It gives you the right result. Okay. So instead, what if we put in a bigger value in here? For example, if you put in 100, 100, and 101, if you run this code again, you can find that we're getting not a number in here, right? So what's happening here? Again, it is because the floating point number have limited precisions. And if we go ahead and directly take exponential with respect to 100, this value is going to explode, right? Because we, with the number of bits available, we are really not able to express this number in the memory. Okay. So what can we do to avoid this case? And there's an approach that we can do to avoid this called numerical error. And the way that we do this is you can find that actually there's an invariant in here. So if you have an exponential of xi, and if you're subtracting each of xi by a constant value c, you'll find that actually the computation does not change. However, we can leverage this fact to try to scale, try to actually change the value of xi so that they become a small value as opposed to a very big value, because we're taking an exponential of something, say, smaller than 0, usually it's much more accurate than taking exponential of a very big number. So what we can do is we can try to take c to be maximum of all those x, so that we will be able to, so that actually after this transformation, all the values are going to be negative, and except one, that's going to be 0. So in order to perform this, what we can do is we can try to take x, we're going to subtracting x by the maximum values in here. That's performing this transformation. And then we're going to run the same exponential normalization again. And if we run this, and then can provide a very big number here. And what you'll find that it actually gives us kind of a stable result. It's no longer going to overflow. Okay, so similar principles apply to other operators like log softmax operator and log sum exponential operator. Both of them are quite widely used as part of normalization process in our end-to-end flow. Okay, so so this is the stable computation of softmax, and that is the approach that we can use to implement some of our homework. So of course, in certain cases, right, in this case, we kind of need to be aware of the fact that we are computing softmax and we are providing a numerically stable implementation of that softmax operations. For advanced computation graph system, we might be able to also go ahead and detect the computation where such kind of overflow can happen and try to automatically renormalize it to enable stability. But that's kind of an advanced topic. Maybe you can take as part of a project, and we wouldn't require that as part of our homework implementation. Okay, so we've talked about some of the basics, and now let's start to talk about how we can design a neural network library on top of our current set of implementation. Remember that as part of your homework 1, we're only implementing a tensor class, right? As well as arithmetic computations along the tensors, such as we can do additions, subtractions. We're also able to do things like doing automatic differentiation or backward function, which is what you implemented as part of your homework. In the last lecture, we also talked about at high level what are the important components of the neural network library. So we know that there's a module that can help us to compose up models. We can also use a module abstraction to build loss functions. We will need to be able to help us to initialize the weights using different initialization functions. Let's optimize it. It specifies how do we take parameters and update gradients. And there's also data loading and pre-processing function. So today we're going to go ahead and implement some of those. In particular, we're going to focus on the end of module. Okay. So let's start with module interface, and I'm going to do a bit of coding together with everybody here because coding can be fun. So in order to get the module, the first thing that we need to get is this parameter class. We kind of already have it here, right? So we have this parameter class. So in this case, this parameter class is a subclass of tensor. And the only reason why we need this parameter class is we just need a way to indicate this is a special kind of tensor, which is called parameters. And we want to have a way to be able to say that in certain cases, we want to be able to say that W is instance of parameter. So effective parameters have nothing, there's nothing special about parameters, and you don't even have to specify a constructor of it. It's just a way to know that hey, this is a special kind of tensor called parameter. Okay. Now with this special kind of tensor, we are ready to introduce a module class. Okay. So a module class contains a few things. The most important function of module class is this function called parameters. And it defines how are we going to go ahead and pull all the parameters from this particular module. And in order to do that, we need to define an accelerator function called getParams. And that contains a value. And I'm going to implement this, and I'm going to walk you through this after I finish the implementation. The first thing I'm going to check is if is instance value parameter. If it's the case, I'm going to directly return value. Okay. Then the second case, if it's instance value dictionary. In this case, we're going to go ahead iterate over all these items of this dictionary and return get primes. So we're going to say result equals a list. Result that's equal get params b, and we're going to return b in here. Okay. And there's a third case where actually we're not going to return b, we're going to return the result. The third case is we're going to check if value is instance of module itself, and if it's a module, we're going to return value dot get dot parameters. And in here, what we are going to do is we're going to do return get params self dot. So this dict is a special attribute of a class, right? It tries to gives you every member of this class. And so effectively what's happening in here is that we want to allow these parameters to be able to pull up these all the classes that are subclasses of parameters and return that to the inputs, right? So what you can find what it does here is it try to recursively look into the value called get parameters, and then trying to be able to find the corresponding parameters and return them as a list. We can go ahead and actually try to create some modules to see what is the effect of it. So let's assume that I want to say create what we call scale add, which is a subclass of module. And in the scale add modules, we're going to define two parameters in here. The first parameter is going to be a s factor. So let me define two. S equals 1, initial b equals 0. Let's say we have self dot s equals parameter init s the type equals float 132, and I have self dot b equals parameter init b, the type equals floating point 32, and then okay, so in here, besides the parameter function, actually we also want to define a call function, which simply redirect it to self forward. Okay, so after running this, and here I can define a forward function as input x. What we're going to do is we're going to return x times self.scale plus self.b. Okay, we're going to find that this is effectively a one neural network module that we can create, and we will be able to create one instance of it by calling scale add. And there are a few things we can do with this module. Right? So the first thing we can do is we can say scale add dot parameters. And if we look at this, you can find it returns a list of two tensors. As a matter of fact, this scale add parameters correspond to these two fields, self.s and self.b. And so why does the parameter return this? We look at the implementation, right? You can find that effectively the self.dictionary of that scale add contains s, that s value, right, and b, that b value in here. We get this dictionary being passed on to this function that goes into this code parse that unpacks it and called get params. And for both cases, the value itself is a parameter, right? So get pulled up. If I have other values that are not parameters, they wouldn't get pulled up to the output in here. So this parameter function is a very convenient method for us to pull out recursively all the fields that are corresponding to parameters in here. And you will even be able to go ahead and check. For example, you will be able to say that this dot 0 is s add dot s here, which is true. And this dot 1 is s add dot b. Right, so you can find that indeed this parameter corresponds to this two field, the s and b. Another thing we can do is, now we have this module, so we'll be able to go ahead and try and apply it. Tensor 2, the type equals 32. If you apply it, you can find that the value is going to be another needle tensor. Let's see. Okay, so this should be return, right? So I forgot this return value in here. Let's go ahead and try again. And if you run this, you'll find that it's going to return you a needle tensor. In this case, because scale initially is 1, so it's going to give you the same tensor. But if I parameterize initial s to be true, run again, you can find that equals 4. Right? So if I parameterize by 2, 1, and it's going to give me 5. Right? So effectively for a module, there are two things we can do. We will be able to query, actually recursively query what are the underlying parameters that are contained in that module. The second thing we can do is we can go ahead and take some of these input tensor and apply that. It gives you the output tensor. So now we have defined a scale add. Another thing that we can do is we will be able to actually recursively define modules with respect to other modules. That's a very useful ability in here. So let's imagine that we want to define something called multi-pass scale add. It's also a module. And effectively, what I try to do is try to have two individual pathways. So we have inputs here, x. That's going to go through a scale add pathway and another scale add pathways. And in the end, we're going to add these two things together, and that's my output. So this is my multi-pathway scale add. Of course, realistically, it doesn't mean anything in here. Right? We are only trying to use this as a demonstration of how you can go ahead and compose module together, and you will be able to use the same way if I'm to develop a residual module in your homework. Okay. So in order to do that, the first thing we can do in here is we will be able to define your constructor class. In this case, we'll have two passes. Pass 0 equals scale add, self.pass1 equals scale. Okay, so we kind of get two paths. And in a forward function, we can say that I want to return self.pass0 apply to x plus self.pass1 apply to x. Okay, that's our multi-pass scale add, and we will be able to say mPass equals multi-pass scale here. And again, in this case, I will be able to try mPass dot parameters. From this, you can find that we're getting 4 tensors in here, right? So even though in this case, this module do not have an immediate triad field that contains a parameter, what I try to do is actually what I call more mPass of parameters, because we know that this module contains some of the submodules, right? Self.pass0 and self.pass1. So recursively call the parameters of self.pass0 and self.pass1 to get their parameters. As a result, we are collecting all the parameters of this module recursively. And this is going to be helpful when we are going to introduce optimizers and go ahead and update the weights in here. Okay. So, and we can also go ahead and try. So in this case, actually, this one, the first parameter, we can go ahead and check what it corresponds to. It actually corresponds to mPass dot pass0 dot scale. And the second parameter corresponds to mPass dot pass0 dot bias, and so on. Okay. So now we have this. We will also be able to do things like mPass directly apply it on needle.tensor 1 b type equals 40.32. That gives us the corresponding output. In this case, we have 2 passes. We add them together, it's 2. Okay. So now we have defined all this, right? The next thing we can go ahead and try to do is to define a loss function, because once we have the modules, we want to be able to compose it together with loss function so we can perform gradient update. So in order to define loss functions, we know that loss function can be defined as a module. You already see the implementation in here. So in this case, loss function is a module that does not contain any parameters. In this case, this particular loss function will take in 2 things. It will take in input, which is the output prediction of my overall pathways, as well as the label y that corresponds to the loss value. And the way we compute loss function is we're going to go ahead and compute effectively the difference between the two. Again, the negative one is the artifact of us not having subtraction operators. If you have a subtraction operator, you will be able to go ahead and directly say z equals x minus y. And then you are relating this square loss in here. Right? So in this case, we are simply defining an L2 loss that computes the difference between 2 values. Once we have a loss function, we'll be able to write y equals a label in here. And then in this case, right, let's say x equals 2, and if we apply for mPass, the end result is 4. And then let's assume that we have a label, which is true. What we can do is we can go ahead and first compute mPass that gives us the output of the hypothesis. And then we're going to use a loss function to compute the loss value. So if we go ahead and run it, you'll find that the loss value equals 4, because the forward prediction of a value equals 4, and then the expected value equals 2, right? Difference of the square there, the value equals 4. And if you go ahead and do loss dot backward, we're going to get the gradient values of each of the weights. And actually, we'll be able to go ahead and verify that. So we can go ahead and launch things like parameters equals mPass dot parameters. In this case, actually, each of the parameters will come with a gradient field. So we'll be able to say that param0 dot gradient value equals 8. And if you look at, actually, this also effectively is the path 0 dot scaling dot gradient, right? So y equals 8. We can go ahead and compute the loss. So because we know that it's, the loss value is 4, right? And then, if you think about how we're going to backpropping that, the gradient values with respect to x in this case is going to equal, let's say, first of all, the gradient value of the loss is going to equal 2 times z. Right? In this case, the value z equals 2 in here. So as a result, the gradient value with respect to x equals 4. Let me see if that's right. Oh, it's really hard to compute this manually. Let's see. The loss value equals 4 because this square. So the gradient value equals 2 times 2, which also equals 4. And is the gradient value right? Oh, yes. And because my input is x is 2, right? So again, it's 4 times 2. So the gradient value equals 8. So, okay. So actually, we are indeed getting the right gradient in here. Yeah, so once we have this gradient, we'll be able to go ahead and take a loss function and write up this optimization rule. So we'll be able to say that for ij in parameters, w dot data equals w dot data plus minus learning rate times w dot gradient. You can find that one thing that's really convenient about in-place update is that every time we are doing updates, we directly set the gradient values back onto w. And those w's are still contained, right, within the original module. So the second time when we call forward, they are still going to be in there with the same w field. So we don't need to be worry about how do we pass the new weight value back onto the model ourselves. Okay. So now we have talked about modules. The next thing we're going to talk about is how we can define an optimizer interface. And an optimizer kind of help us to be able to perform updates like stochastic gradient updates and other updates in here. And there are two important functions of an optimizer. The first function is called a reset gradient. So first of all, an optimizer is going to take in a list of parameters that that effectively get passed from module.parameters in here. So once we have those parameters, there are two things we can do. The first thing is reset gradient. So it will simply iterate over all the parameters and reset the p.gradient field to be none. The second function is called step function. So in this case, it iterates over all the parameters. We'll take all the weights and perform one step of updates in here, either stochastic gradient descent or like stochastic gradient with momentum, depending on the update rule we are looking at here. So we can go ahead and try to implement a variant of optimizer in here. Okay. So let's imagine that we have. Let's go ahead and implement the simplest one. We do SGD. It's a subclass of optimizer. And we'll be able to say that in the init function, it's going to be there's a learning rate and there's parameters in here. And then it's going to recall self dot. Well, I'm going to call my parents initializers, right? So super optimizer. I kind of forget what's okay. So actually, I can directly do initialize. That's fine because in this case, the initializer is not as so. I can just do self dot primes equals primes. Self dot learning rate equals rate, and then in the step function, we can do for w in self dot params w dot data equals w dot data plus minus self dot learning rate times w dot gradient dot data. So this is going to be the stochastic gradient optimizer. And we need to define optimizer first here. Thank you. Okay, so now we have implemented this SGD optimizer. The next thing we can try to do is we can try to put everything together, right? Try to run things end to end, see how does things work together. Okay, so in order to do that, what we can do is we can try to build this code block that have been written here. The first thing that we can try to do is we can try to create true needle tensors where x correspond to my input and y correspond to my label tensor. And then we can create a model that corresponds to my hypothesis class that corresponds to a neural network module. In this case, I'm simply using multi-pathway scale at in this case. And the loss function. In here, we're going to use a L2 loss. So next, what we're going to do is we're going to create an optimizer. In this case, SGD is going to be the optimizer we're going to use. And then we're going to run it through a number of epochs here. So each of the epoch, what we're going to do is we're going to first call optimizer.reset gradient. And then we're going to call the hypothesis.model. So model X, that gives you a hypothesis. And then we're going to create a loss function that computes a hypothesis and label. That gives us a loss. And effectively, this is a training loss that we can go ahead and print it out. And we're going to call loss.backward. That gives us the gradient. Finally, opt.step gives us the one step of SGD update in here. Right. So we can go ahead and try run this code block. And you can find actually the loss decreases in here, which means that indeed there is a right amount of training epochs to help us to be able to build those end-to-end neural network training. So I'm going to pause here a bit. I would like everybody to think about what is the difference between this piece of code versus, say, the code that you have been written in your homework 0, where we are kind of effectively derive the gradient from hand and write up the update rule in C++ by scratch. If you look at this particular piece of code, you can find it's very modular. Right? So we'll be able to imagine I want to change my hypothesis. I just need to change this line. Without changing any other parts, it's going to work out of the box. If I'm going to change my update rules like SGD, I can just go ahead and change this particular line of optimizer, right? And the same code structure is going to continue working for a lot of cases. And if I'm going to change my loss function, I'm going to have to change this line. So this code is very modular. They help us to be able to replace different components as we need it. And that's kind of like amazing part about deep learning framework. That gives us ability to be able to mix and match different modules together. And one of the reasons is that we're designing those modules in a way so that they can effectively interact with each other organically. And if you come back and look at those designs, you can find those designs look so obvious, right? They are so simple and elegant. On the other hand, if you put yourself into the time where this design does not exist yet, or in the first generation of deep learning framework, you may find that actually they are not as obvious as it seems. And it's really important to appreciate this kind of modular design and how they compose together. One of the things I want to notice that we only implement SGD, right? So on other cases, we will need to be able to create states in SGD or in optimize as well. For example, if we want to implement something like SGD with momentum, in this case, we will not only need to record the set of parameters, but we also want to be able to create the additional states in here, right? So that we can keep track of momentum variables. So for example, we will need to be able to write things like self.momentum. Say, let's use U to denote momentums. It's equals, needle.tensor zero. Actually, I can do things like needle.zeros like P for P in parentheses. So it will help us to create a set of momentum variables, right? Then we can use to in our update rules. So when we start to create more advanced optimizers, we want to be able to keep track of those internal states within the optimizer class. And that's also one of the interesting part about the optimizer design, where we have the module that contains the parameter states. We have the parameter function that collects out the list of parameters. And then we use this, we recreate those additional auxiliary states that help us to run the corresponding updates. Okay, so that's end-to-end flow. In the next part, I'm going to quickly go over initialization. So in this case, as part of the homework, we will need to implement an initialization function for weights in things like linear transformation and other transformations. In order to derive the overall initialization magnitude of the random initializations, one of the things that we need to remember is in a very deep linear neural networks, every time when you apply a transformation, the order of magnitude of the value can change according to the weight. And one of the goals in here is we really want to derive initialization such that if you are going to initialize things randomly, and your input is also randomly distributed, your output variance is going to be close to your input variance. And there's a derivation from the original paper that effectively says that my output variance is going to equal the second order 2 norm of inputs of each of input and the variance of W. In this case, let's assume that we are doing Gaussian initialization of W. The variance equals sigma squared. And also let's imagine that if X squared is a result of a ReLU activation of previous layers, we know that the result of the variance of ReLU, because you get kind of like the original value on the right hand side and 0 on the left hand side, so kind of get half of variance in there. And our goal is to make sure that the variance of the next layer equals the variance of previous layer. So we'll plug that back and derive the sigma. You'll find that you can have a value to set the sigma according to the number of input fan-ins of your input weights in here. If you change your distributions to things like uniform distribution, we will need to use a similar rule, except that you want to use the variance calculations for uniform distributions. Okay, so we have talked about the overall modules and initializations and how does loss function and everything fit together. So in the last part, I'm going to quickly note about it's kind of a bonus content on tuple values. So if you open up your code in on the right hand side, actually the lecture 8 code now contains additional implementation of tuple, of a tensor tuple. Let's see. Of a tensor tuple that corresponds to a tuple of tensors. In this case, we are not supporting nested tensors, as well as some operation that correspond to tensor tuples, such as getting value from tuple and concatenating tuples together. It also allows us to be able to define operators that whose return value are tuple values. So if you look at ops in here, actually we have this operator called fused add scalar. Effectively, it's in the compute, it's going to return 2 values as opposed to 1. And the output gradient actually in this case is a tuple. And in our case, we want to, because A is present in both cases, we're going to add those 2 gradients together. Okay. So one thing you will find is that with the same autograph mechanisms, we will be able to create a tensor, run it through a tensor operator that gives you a tensor tuple, and actually continue to gives you tuple values, and you will be able to obtain the elements of the tuple values. So you are more than welcome to check it out, and it is a very useful way for us to express a operation that contains multiple return values. And the same mechanism, it's amazing to see that same automatic differentiation mechanism actually works out of box in here. So for example, I would be able to say that v0 equals z0 plus z1 times 2 and b0 dot backward. And it should be able to, backward. It should be able to propagate the gradient back onto x properly. And if you are more than welcome to go and check it out. And if you are interested, of course, not part of the requirement, you are more than interested, you are more than welcome to implement, say, automatic differentiations for other data structure values like dictionaries and so on. Okay, so that's the end of this lecture. Thanks everybody for coming, and I will see you folks in next few lectures.